Hello, my name is Tomasz Lizurej, and I'd like to present our work Efficiently Testable Circuits. This work has been done together with Mirza at Baig, Suvradip Chakraborty, Stefan Dziembowski, Małgorzata Gałązka, and Krzysztof Pietrzak. We consider the problem of tampering the circuits. A device implementing a functionality F is given, and then it's handed to some adversary, and this adversary may tamper with the device. Finally, the device is given to the end user and may be installed in his device. And the question is whether this device still implements the functionality F. What is the tampering model that we assume? The tampering model was actually introduced by ISTA et al. In their work Private Circuits 2. In the model, a Boolean circuit is given and described with a DAG. And then the adversary is able to tamper with the wires of the circuit by setting each wire to a constant 0, setting it to a constant 1, toggling it, or doing nothing with the wire. We also assume conductivity assumption introduced by ISTA et al. In our work. In the conductivity assumption, we are given wires which are copied to n distinct locations. And the adversary is able to apply only one tampering to all subparts of such wires. Whenever the wires are copied to at most n locations in the whole circuit, we say that the circuit is n-conductive. Of course, the trivial solution to protect against errors which come up in circuits tampered in such a way is to do brute force testing. By brute force testing, I mean that one could check how the circuit behaves given all the possible inputs to the circuit. But we assume that these circuits may have large input size, even more than 100 input wires. There are two major lines of work which are related to our work. The first one is the already mentioned Private Circuits 2. In their work, they encode each wire into two wires, to either 0, 1 or 1, 0, and then they secret share each original input wire. Finally, whenever some error occurs, this error will be cascaded through a cascade of gadgets into the output, which means that whenever an error occurs, the output of the circuit will be zeroed out. Their setting is secure against any number of set to 0 tamperings or less than t arbitrary tamperings, where t is the size of the mentioned secret sharing. The second line of work that is related to ours is on heuristic testing. These works stem from hardware testing community, and they are focused on testing against benign, non-adversarial errors which are created during the production phase of a device. Some heuristics are given in a well-established literature, for example this book cited on this slide, and they give presumably high rate of success given some distribution of errors. But it's never 100% and never assuming adversarial errors. In our work, we propose a compiler for circuits and a testing procedure. We assume adversarial errors, and we assume that adversary may introduce any number of these errors into the circuit. And then the compiler compiles a circuit into a one which is only constant times larger than the original. And of course, we proposed an efficient testing procedure for the compiled circuits. In our approach, we give a compiler that compiles any circuit C with S input bits and T output bits into a pair C hat T hat, such that this C hat is a new circuit with additional S' and T' input and output bits, and T hat is a testing set, which is a subset of all possible inputs to the new compiled circuit. And then this new circuit must be functionally equivalent to C, which means given any input to the original circuit, the compiled circuit will output on the first T output bits something equal to the output of the original circuit. What is more, this pair C hat T hat must be testable, which means for any tampering tau applied to wires of the circuit, whenever there is some inconsistency on the outputs of the compiled circuit, then the inconsistency can be also detected by going through the inputs of the testing set. This property implicitly gives us efficient testing procedure. In the following slides, we will present the construction of the compiler based on some very simple example. The example will be given for a function x1 and x2 or x3 and x4, and it will be described with such simple Boolean circuit. Before we present the actual construction of our compiler, we will present the idea of covering sets. The covering set T is a set such that every wire of the circuit is evaluated to both 0 and 1 given some inputs from T. In our example, the covering set would be simply all zeros input and all ones input. But in general, this covering set might not exist or even be hard to find for some complex circuits. But whenever we have some C for which the covering set is hard to find or even impossible to find, then we can preprocess it into a pair C' T'. The C' will be a new circuit functionally equivalent to C, and C' will have covering set T'. And how do we achieve this? We achieve this by modifying evaluation of output wires of some gates by adding XOR gates to their input wires. And these XOR gates will be connected directly to some new input bits, which we call control bits. So let's say we have an AND gate. Its inputs are already covered, which means that they are evaluated to both 0 and 1 given some inputs. But maybe they never get evaluated to 1 at the same time, which means we never get 1 at the output of the gate. Now, when we add a new XOR gate connected to some control wire, then this XOR gate may make the right input wire evaluate to 1, and then at some point the output of the AND gate can also get evaluated to 1. In general, we will need only 3 control bits to preprocess the whole circuit. Now we will present some trivial solution to our problem. We are given a circuit C with a covering set T, and what we do, we output all intermediary values in the circuit directly to the output of the circuit. And because we have the covering set T, what we can do input-output testing on all elements from this covering set T. Now, whenever we have some topologically first tampering in the circuit, and we know that this wire will be evaluated to both 0 and 1 given some inputs from the covering set T, then there must occur an error during the evaluation. And because this wire is conductively attached to the output of the circuit, this error will be also detected directly on the output of this circuit. This construction remains 2 conductive whenever the input circuit was 1 conductive. The drawback of this construction, however, is that it outputs too many output bits to the construction. Normally, we assume that the circuit has around 100 input and output bits, and it can have around 1 million gates inside. This means that we would need to add around million output wires to the circuit, which is an unrealistic assumption. In the following slides, I will present how to decrease the number of the output pins in such construction. The current slide presents a partial solution to the problem with a decreased output size of the compiled circuit. So we are again given a circuit C with a covering set T, and what we do is we connect all the intermediary values in the circuit to chains of AND and OR gates. Let's assume at this point that these chains themselves are not tampered. Of course, the input wires to these chains can be tampered, but the intermediary values in the chains and their output pins cannot be tampered. We again do input-output testing on the modified circuit on all elements from the covering set T. And the solution will again detect topologically first tampering that will produce some error. And because this error is evaluated to both AND and OR chain, then for example, when we know that all the wires of the circuit should be evaluated to 0, and an error occurs that evaluates some wire to 1, then this wire will connect to the OR chain, and because we know that the output of the OR chain should be 0, and we have the error will switch the output of the OR chain. This construction remains free conductive given a circuit that was 1 conductive at the very beginning, because each wire is connected to 2 gates, 1 gate from AND chain and the other gate from the OR chain. In the following slides, I will say how to get rid of this assumption that these AND and OR chains cannot be tampered to make sure that the construction is secure. Before we proceed, I will introduce the multi-OR gadget. Actually, it's a chain of OR gates connected to a single control bit at the very beginning. And given C equal to 0, the gadget still computes the OR of the inputs of the gadget. But if any of the input values is tampered to 1 at some point, and we know that all of them should be 0, then the multi-OR will not switch when we switch the control bit. But naturally, when all of the input bits should be 0, switching the C should also switch the output of the gadget. Analogically, we can define the multi-AND gadget. Now I will present the first full solution to our problem. So in the previous construction, we will replace the chains of AND and OR gates by the multi-AND, multi-OR gadgets simply by adding a control bit. And given some input from the testing set that evaluates maybe all the wires of the circuit to zeros, we know that whenever some tampering occurs in the circuit, and this topologically first tampering may, for example, set this wire to 1, we will see that one of the chains, like the multi-OR gadget, will not switch its output given switching control bit. Actually, we can do such evaluation in the testing phase by simply adjusting the covering set by adding all evaluations of the control wire to the testing inputs. Analogically, we can describe our functionality in terms of the multi-AND gadget. The drawback of the construction, however, is its large depth, produced by the long multi-AND, multi-OR chains. And how do we decrease the depth of our construction? We apply some recursive strategy with L layers, where L is a small integer value. And the example will be given for 2 layers. And how do we construct another layer of our construction? When we have 2 layers, we will divide the long chains into shorter parts, subparts of square root of n length. So we will have square root of n such subparts. And we will connect these subparts to the chains of AND and OR in the next layer. Now, when we switch the C bit in the first layer, we know that appropriate chain, for example, OR chain, should switch accordingly. And then, to again detect whether the outputs switch properly in the second layer, we apply the new control bit that detects a similar property in this layer. We can realize this testing process by simply adding all evaluations of both control bits to the original inputs of the testing set. The depth of the circuit rises at most L times Lth root of n with L layers of the construction. And what about the parameters of a construction? Assuming a circuit with input size S, output size T, number of gates N, and circuit depth D, after preprocessing, we will add only 3 new input bits, and the size of the circuit will rise only at most 3 times. The circuit the circuit depth will rise only logarithmically. Now, when we will finally compile our circuit with L layers, we will again add L new input bits, 2 to the L output bits, but the size of the circuit will rise only linearly, and the circuit depth will rise only L times Lth root of 3n. The test size will remain small because of the small L parameter, and it will be 4 times 2 to the L. We strongly encourage you to continue the study of the tampering models. The first thing that one could try to do is to remove the assumption of conductivity. We have already solved this problem in some other work, since we put it as our priority after finishing this work. We will try to publish the results soon. The second problem is the problem of gate tampering. In the problem of gate tampering, one could assume that the adversary could switch current gates with some other gates, but the topology of the circuit would still remain the same. The third problem is the idea to allow modifications of the topology of the circuit. For example, by adding new gates to the circuit or removing some of them from the circuit. Thank you for your attention.